Space, the final frontier, a vast, unending expanse of mysteries waiting to be unraveled. Since the dawn of mankind, we've looked up at the stars with wonder and curiosity. This inquisitiveness propelled us from mere stargazers to explorers charting the unknown realms of space. From the first human orbiting Earth in the 60s to the giant leap for mankind with the moon landing, we've been pushing the boundaries of what's known and unknown. And let's not forget the tireless Mars rovers, our mechanical emissaries, traversing the red planet's surface, unearthing secrets buried in time. Each of these milestones represents a triumph of human ingenuity and a testament to our thirst for knowledge. As we stand on the precipice of the unknown, we ask, how far can our spacecraft actually travel? To understand our boundaries, we first need to understand our vehicles, the spacecraft. These marvels of engineering have allowed us to venture beyond the confines of our planet, but they're not without their limits. The modern spacecraft are propelled by rocket engines, which rely on the principle of action and reaction. These engines burn chemical propellants to create a high-pressure and high-temperature gas, which is expelled to generate thrust. However, these traditional chemical rockets have their drawbacks. They are limited by the energy content of their propellants, which in turn limits the speed at which they can propel a spacecraft. The fastest spacecraft ever launched, the Parker Solar Probe, reaches speeds of approximately 430,000 miles per hour. Despite this impressive speed, it would still take the Parker Solar Probe about 6,800 years to reach the nearest star to our solar system, Proxima Centauri, which is about 4.2 light-years away. Moreover, these systems are inefficient in terms of fuel consumption. A significant part of a spacecraft's weight is fuel, and once it's used up, the spacecraft can no longer change its trajectory. This is a critical limitation for long-duration missions, as it restricts the ability of spacecraft to explore far-off celestial bodies in a single mission. Additionally, the force exerted by these rockets is only temporary. Once the fuel runs out, there's no way to generate more thrust. This means that spacecraft must rely on gravity assists or orbital maneuvers to adjust their course, which requires careful planning and limits flexibility. There's also the issue of wear and tear. Spacecraft engines must endure extreme conditions, including high temperatures and pressures, which can lead to material degradation over time. This limits the lifespan of the engines and, by extension, the spacecraft itself. While we've come a long way, these limitations remind us of the challenges that lie ahead. As we continue to push the boundaries of our cosmic neighborhood, we must also push the boundaries of science and engineering, developing new technologies that will allow us to travel further, faster, and more efficiently than ever before. In space travel, speed and direction matter. Let's talk about escape velocity and orbital dynamics. Escape velocity is the speed a spacecraft needs to break free from a planet's gravitational pull. It's like a cosmic speed limit that dictates whether a spacecraft stays stuck in orbit or heads off into the vast expanse of space. Now, on to orbital dynamics. This is the study of how objects in space move and interact under the influence of gravity. It's a bit like choreographing a cosmic ballet, with every spacecraft, planet, and star playing a part. It involves precise calculations to ensure our spacecraft take the most efficient route, conserving fuel and time. These principles, escape velocity and orbital dynamics, are the keys to unlocking the mysteries of our universe. They help us plan space missions, navigate around celestial bodies, and even predict future trajectories. Understanding these fundamental principles is crucial in charting our course through the cosmos. Before we reach for the stars, we must first conquer our own backyard, the inner solar system. This is where our journey of discovery begins, a journey that has taken us to some of our closest celestial neighbors. First up is Mercury, the smallest and innermost planet in our solar system. Despite its proximity to the Sun, it's been a destination for only 2 missions: NASA's Mariner 10 in the early 70s and the Messenger probe, which orbited Mercury for 4 years before concluding its mission in 2015. These missions unveiled a world with a surprisingly dynamic geological history. Next is Venus, our sister planet. Despite its inhospitable surface conditions, it has been a popular destination for spacecraft. Soviet Union's Venera missions in the 70s and 80s even managed to land on the surface and send back images, a remarkable achievement given the harsh environment. Then there's Mars, the most explored planet in the inner solar system. From NASA's Viking landers in the 70s to the recent Perseverance rover, Mars has been a focus of our quest for signs of life beyond Earth. These missions have provided invaluable insights into the red planet's history and potential for habitability. Our journey doesn't stop at the planets. We've also visited the asteroid belt, a region of space between Mars and Jupiter filled with remnants from the early solar system. NASA's Dawn mission, for example, studied two of the largest objects in the asteroid belt, Vesta and Ceres, revealing clues about the formation of our solar system. These missions have pushed our boundaries, but there's still much more to explore. As our technology improves, so too will our ability to uncover the mysteries of the inner solar system. Whether it's delving deeper into the Martian surface or visiting unexplored asteroids, the inner solar system continues to be a rich field for exploration, a stepping stone to the far reaches of our cosmic neighborhood. As we venture further from the Sun, the challenges multiply. The outer solar system, home to gas giants like Jupiter and Saturn and ice giants like Uranus and Neptune, poses a unique set of obstacles for our spacecraft. One of the biggest challenges is the sheer distance. To give you a sense of scale, it took Voyager 212 years to reach Neptune. That's over a decade of travel at an average speed of 56,000 kilometers per hour. These long distances also come with extended communication times. When a signal is sent from Earth to a spacecraft near Neptune, it can take about 4 hours for the message to arrive. And then another 4 hours for the response to come back. That's an 8-hour round trip for any command or data exchange. Additionally, the further our spacecraft travel, the less sunlight they receive. This reduces the effectiveness of solar panels, a common source of power for many spacecraft. The harsh, cold environment of the outer solar system also places a strain on the spacecraft's systems and instruments, requiring robust design and innovative solutions. Then there's the matter of navigation. With fewer landmarks to guide the way, navigating the outer solar system can be like finding a needle in a haystack. And let's not forget about the increased radiation levels, which can damage spacecraft electronics and shorten mission lifetimes. But perhaps the most significant challenge is time. With current technology, missions to the outer solar system take many years, even decades. This requires long-term commitment and planning, and the spacecraft must be designed to operate and survive for extended periods in the harsh conditions of space. And yet, despite these hurdles, our curiosity propels us forward. We continue to push the boundaries of our knowledge and capabilities, venturing further into the cosmos. The outer solar system remains a frontier, a place of mystery and potential discovery, and it is these challenges that make the journey all the more worthwhile. Let's journey to the edge of our solar system with the New Horizons mission. In 2006, Earth bid farewell to a spacecraft destined for the farthest reaches of our solar system, New Horizons. Its mission? To fly by Pluto and its moons, providing the first close-up views of these icy worlds. The journey was not without its challenges. Traveling at blistering speeds of over 58,000 kilometers per hour, New Horizons had to navigate a path through the Kuiper Belt, a region of the solar system beyond Neptune filled with icy bodies and remnants from the formation of the solar system. This was no easy task, but the team behind New Horizons was up for the challenge. The spacecraft, equipped with a suite of 7 scientific instruments, was designed to capture high-resolution images and collect data on Pluto's atmosphere, surface, and moons. As New Horizons approached Pluto in July of 2015, it began its investigative work, turning its instruments towards the dwarf planet and its largest moon, Charon. The data collected by New Horizons during this flyby provided invaluable insight into these distant celestial bodies. Images revealed a diverse and complex landscape on Pluto, with towering mountains of ice, vast plains, and deep canyons. On Charon, they found a young surface, suggesting geological activity. New Horizons' journey didn't stop at Pluto. The spacecraft continued on, conducting a flyby of Arrokoth, an ancient Kuiper Belt object, in January of 2019. This extended mission further broadened our understanding of the outer solar system. Today, New Horizons continues to travel, venturing deeper into the Kuiper Belt. It's an ambassador from Earth, carrying a message of exploration and discovery into the uncharted regions of our solar system. The New Horizons mission has shown us that the outer solar system is within our grasp. It serves as a testament to human ingenuity and our relentless pursuit of knowledge. As we look to the future, we are inspired by the accomplishments of New Horizons, eager to see what new frontiers await us beyond the horizon. So, what's next for our cosmic journey? As we contemplate the future of space travel, we can't help but marvel at the potential of proposed interstellar missions like Breakthrough Starshot. This ambitious project aims to use light sails propelled by powerful lasers to send tiny spacecraft to our nearest star system, Alpha Centauri. The idea is to reach speeds of up to 20% the speed of light, enabling us to reach these distant stars within a human lifetime. However, the challenges are immense. The spacecraft need to be extremely light yet robust enough to survive the harsh conditions of interstellar space. The lasers required to propel them would need to be incredibly powerful, far beyond our current capabilities. And even if we overcome these hurdles, the tiny spacecraft would only be able to send back a limited amount of data due to their size and distance from Earth. On the other hand, advanced propulsion technologies like ion propulsion offer a more immediate and practical solution for extending the reach of our spacecraft. Ion propulsion works by electrically charging or ionizing a gas and then expelling the ions to create thrust. Although the thrust is tiny, it can continue for a long time, gradually accelerating the spacecraft to high speeds. This technology has already been used successfully in several missions, and its efficiency and longevity make it an attractive option for future deep space exploration. And then there's the concept of light sail technology, a promising idea that's been around for a while but is gaining renewed interest. Light sails work by using the pressure of sunlight to propel a spacecraft, much like a sailboat uses the wind. The advantage of this method is that it doesn't require any fuel, which makes it ideal for long-duration missions. The challenge, however, lies in creating a sail that's both light enough to be pushed by sunlight and durable enough to withstand the rigors of space travel. As we innovate and push the boundaries of technology, the stars might not be as far away as we think. The future of space travel holds exciting possibilities, full of challenges to overcome and new frontiers to explore. Exploring space is not just about the journey, but also about the communication. The vast distances separating us from outer space present incredible challenges. Our current communication methods are stretched to their limits as signals take longer to travel these immense distances. For instance, a simple message from Mars to Earth can take anywhere between 3 and 22 minutes, depending on our planet's positions in their orbits. Now, imagine the time it would take for a message to reach us from the edge of the solar system or beyond. Such delays can cause significant problems, especially during critical mission phases. Imagine piloting a spacecraft through an alien landscape with a 22-minute delay between your inputs and the vehicle's responses. It's not just impractical, it's nearly impossible. As we push farther into the great expanse, we'll need to develop new ways to communicate effectively and efficiently. Quantum communication, for example, is a burgeoning field that could potentially allow us to send information instantaneously, no matter the distance. But as we grapple with these technical hurdles, we must also consider the profound ethical implications of our journey. Are we ready to encounter extraterrestrial life, if it exists? And how do we protect other celestial bodies from contamination as we explore them? These questions don't have easy answers, but they are crucial to consider as we expand our cosmic frontier. Space exploration has always been about pushing the boundaries of what's possible. It's about the indomitable human spirit that looks up at the night sky and dreams of understanding the cosmos. But as we venture further into the unknown, the challenges ahead become more complex and multifaceted. As we venture further into the cosmos, we must navigate these challenges with the same spirit of discovery that started this journey. The cosmos is vast, but not unreachable. We've journeyed through the history and present of space exploration, delving into the limitations of our current propulsion systems and the potential of future technologies. We've touched upon the profound challenges of voyaging to the outer solar system and beyond, and the immense promise that lies in advanced propulsion technologies like ion propulsion and light sail technology. We've seen how our Voyager and Pioneer probes have pushed the boundaries of our reach into the cosmos, and how proposed missions such as Breakthrough Starshot aim to propel us further still to neighboring star systems. Yet, with every new frontier comes new challenges, be it in deep space communication or the ethical considerations of deep space exploration. So while the journey is long and the challenges are many, the quest for knowledge continues. Remember, the sky is not the limit, it's just the beginning.